Welcome to note set number 7, where we will start talking about Fourier series. And in this set of notes, I warned you that we're going to be heavily using these complex exponentials, and it's going to continue in this set of notes. So if you're still a little rusty on those complex numbers, you got to get that down quick. So Fourier series is where all the fun starts. And we start seeing some really interesting things about signals as well as systems. So if you remember back a few lectures, I said one of the big ideas about working with linear systems is that if we can break a signal down into some simple components, we can figure out how each one of those components goes through, and then add all those individual responses back up to give us the total response to the actual input signal. Well, this is one way of doing that. What Fourier series tells us is that we can take virtually any periodic signal that we run across in the real world, and we can break it down into a sum of appropriate sinusoids. So these sinusoids can be thought of as building blocks from which we can build any periodic signal that we're interested in. And that is an extremely powerful idea. So we've already shown how easy it is to solve a differential equation, a circuit, a system, in terms of a sinusoid by using phasor ideas. This is going to now say, hey, I can break any periodic signal down into sinusoids. I can then solve for each and every one of those sinusoids, then add up all those individual responses, and I've got the output of a system, circuit, differential equation to a input that's periodic. So we are expanding, slowly chipping away at the kinds of things that we can solve. And that's great. And later on we will extend this same idea. It'll be basically the same idea, except we'll make it even more powerful, and we can do the same thing for non-periodic signals. Then we've got essentially the whole world at our fingertips. Engineers are always thinking about signals as being made up of sinusoidal components. And musicians do this too, and audio engineers. That's why. You hear an audio engineer saying, I need to boost the 500 hertz range. What they're saying is, music and signals are made up out of different frequencies, different sinusoidal components at those frequencies, and if I could somehow take those that are near 500 hertz and make them a little bit stronger, I'd have a signal that would sound better for whatever it is that I'm trying to do. But from a systems point of view, our attention, all this attention to sinusoids comes from what we just saw. Phasor analysis, sinusoidal analysis of RLC circuits. What we learned is this fundamental result. Sinusoid into this system, sinusoid out. The frequency is going to be the same. The only thing that changes is amplitude and phase. Learn this box. Know this box inside and out. That's the biggest idea in this whole course. Sinusoid in, sinusoid out. Frequency is the same. All we need to do is figure out what is the new amplitude and what is the new phase. Look back at that example we did for the RL circuit that we did by phasor. What's the phasor maintaining? It's carrying around amplitude and phase, and we came up with some numbers, complex numbers that came from the impedances that altered the amplitude and phase, and then we rewrote our new sinusoidal output with a new amplitude and phase. That's it. Go back and look at that example and you'll have it. Here is that same RL circuit. Now I'm looking at a voltage in and possibly most likely here a voltage out, but the idea is sinusoid in, same frequency out, different amplitude. A goes in, B comes out, phi goes in, theta comes out. I just have to figure out how A gets to B and phi gets to theta. Phasors allowed me to do that in a very systematic, simple way. But let's take a look at this. We'll motivate this idea further for not just a circuit, but for a differential equation. So here's a simple second order differential equation. Let's motivate this idea. Here's our input sinusoid. So the solution must be such that if I take these derivatives, add them together this way, that it gives me the input sinusoid. So suppose that the solution is a cosine, like we said. So I know that this has to be the solution. We've already established that sinusoid in, sinusoid out idea. So I hypothesize that as my solution. I plug it in, I get cosine, I get sine, I get cosine, I get cosine. So I've got two cosines and a sine that have to add together to give a single cosine. That's where it gets messy to deal with. You can do it, but it's going to take a lot of algebra, a lot of trig identities, and it's just yucky, yucky, yucky. If we go to the complex sinusoid case, it's going to be very, very easy to do this, as we've seen. But we've already seen reason to believe that sinusoid in, sinusoid out is a fundamental result. So for if our input is a linear combination of sinusoids, so suppose we have some sum of sinusoids, a bunch of different frequencies, a bunch of different amplitudes and phases. Well, now by superposition, assuming that we've got a linear differential equation, which is what we're looking at, I can handle each of these terms individually, solve, and then add the results together. So I can then hypothesize that the solution looks like this, but the important thing is these are linked, right? So the first term of the input gives the first term of the output. That's the important idea. So breaking a signal down into sinusoidal parts is a simple way of attacking a problem, if we can assert that our input can be broken down into a sum of sinusoids. And so the big idea that Fourier had, big French mathematician back around Beethoven's time, in fact their lives almost completely overlapped, so that was his big idea. But the question is, what kinds of signals can we use this trick on? So in other words, what kinds of signals can we build by adding together sinusoids? And the first thing we'll see is, well, we can add together sinusoids and make periodic signals. Then later we'll have to modify our idea of adding together, and we'll be able to handle virtually any signal that you'd be interested in signal processing and communications and things like that. So what can we build with sinusoids? So let's start simple. We're going to fix some fundamental frequency, omega sub 0. So the subscript 0 there is giving us that's a specific fixed frequency. And now as our building blocks, we're going to say, let's take all cosines that have frequencies that are integer multiples of omega 0. So we're going to take 1 omega 0, 2 omega 0, 3 omega 0, and so forth. But we'll let the amplitudes and phases be anything that they want to be. So suppose we take omega 0 equal to 30 radians per second. We're going to consider k to be 0, to be 1, to be 2, to be 3, and so on and so on and so on. That's the idea. So to just get an idea of what kinds of things we can build with these building blocks, let's just try this out numerically in MATLAB for a variety of different amplitudes and phases and see what we get. But on this next slide, we're going to just limit ourselves to 3 cases where we have only 3 terms. So let's look at for the example on the next page, we're going to set omega 0 to be equal to 2 pi, and we're going to let k range only over 1, 2, and 3. So this is the signal that we're going to look at, and so we've explicitly said we're creating it with these building blocks, and we're asking what kind of thing can we make? What is x of t going to look like? So let's look at that. Here's an example. Just pick 3 different amplitudes, 3 different phases, and see what we get. So here is the signal x of t. And those vertical red lines, we'll see what role they're playing in just a minute. But even right now, you can look and see that within each block marked by those vertical red lines, we're seeing the same structure. So, aha, this thing is creating a periodic signal. And what is its period? 1 second, right? So 1 second, 2 pi, go away, 2 pi over our frequency, 2 pi is equal to t. So this was our omega 0, and that's equal to 1. So a period of 1. So that makes sense. Our fundamental frequency, omega 0, gives us this period. Well, let's see what else happens here as we go through this example. So let's look at the next one. We're going to keep the phases equal here. And change the amplitudes. Now we get something still periodic, same period of 1 second, but a very different shape. And all we've done is just changed the amplitudes. So now instead of emphasizing the first one, we're emphasizing the middle one. And very much de-emphasizing the lowest frequency one of them. And we get something that looks very different, but also has the similarity of having the same period. And then the third example, now we're going to keep these amplitudes the same, but we're going to change the phases. And again, now it's still kind of the same, fairly similar, but still very, very different. And so this just illustrates, well, let me back up, also still the same period, 1 second. So what this is illustrating here is that just by changing these few parameters, we can get a broad variety of different signals, but they're all periodic with the same period of 1 second, and that 1 second gets tied back to our choice of omega 0, that so-called fundamental frequency. The other thing we see is that they're all centered vertically at 0. So if you were to draw a line through at 0, you'd find the same amount of area above the curve as below. A little hard to see, but you'll have to trust me on that one. So why do these all have period of 1 second? Well, here's the 2 pi, then we have 2 times 2 pi, 3 times 2 pi. Those are the 3 different frequencies. This one repeats every 1 second. That's its period. This one has a period of 1/2, but it also repeats every 1 second because that's 2 periods. This one repeats every 1/3 second, but after we've gone through 3 periods, so in 1 second, it's also repeating that. So they all consistently repeat every 1 second. We're back to where we began. So that's why the sum of them has the longest consistent period of them all. So if for some reason we picked an entirely different frequency here and this 1/2 never got multiplied to be equal to 1, then we would not have a periodic signal at all. But in this case, things are set up so that it's kind of like somebody walking with steps twice as fast, 3 times as fast. Eventually you're going to all put your foot down at the same time, and that will keep happening over and over again. So that's why we end up with a periodic signal, because these are integer related. These things are also related by integer multiples. So this motivates this following general idea, that if we take sinusoids whose frequencies are integer multiples of some lowest fundamental frequency, and we add them together, we'll get a periodic signal whose period t is set by that fundamental frequency, the slowest sinusoid. So now we can extend this idea and say, well, adding 3 together was good. Let's add together an infinite number of them. Keep making this frequency higher and higher and higher and higher, and we can build some pretty amazing things that way. Now, why were those all vertically centered at 0? Well, each term is centered at 0, right? A cosine is simply centered at 0. And so if you have three things that are all centered at 0 added together, their result is also going to be centered at 0. So what this tells us is that unless we add a constant term out in front, anytime we add up a bunch of sinusoids, it's all going to be centered at 0. And we would say that when it's centered at 0, we say it has 0 offset. We also say it has 0 DC offset, as we'll say in a little while. So we take our infinite sum, going over the frequencies, omega 0, 2 omega 0, 3 omega 0, and so on, and then we add one last term, a constant out in front, that will allow us to move this whole thing up and down so that we can have it centered around A0 and set A0 to be anything that we want. So that's nice. So there is our Fourier series. This is a way to build a periodic signal. And if you have this form, you find your omega 0, put it into that formula, and that tells you the resulting period of that periodic signal. And by selecting the appropriate coefficients, the A's and the Phi's, we can create a variety of different periodic signals. And in fact, the claim is virtually any real-world periodic signal you'd be interested in as an engineer, you can create it this way. And that's the real big idea here. We're not going to prove it. It can be proven. The proof is in the book. But basically, the big idea is by adding together infinitely many sinusoids plus this DC term out in front, we'll call that the DC term. You might want to write that down. We can build virtually any real-world periodic signal that we're interested in. And that is a huge idea. So once we've set our fundamental frequency, all we have to do is figure out the right amplitudes and phases to give us the periodic signal that we want. Then, remember, the whole point of this is then all we have to do is analyze our differential equation for each term, figure out how that goes through, and we've got the solution to our system problem. And that is a big, cool idea. So what we need to learn how to do is for a given periodic signal that somebody's saying, this is my desired input, we need to figure out what are the appropriate amplitudes and phases so we can put those here and here, and then analyze our circuit for those resulting values. So there are actually three forms of Fourier series. The one we just looked at, repeated here, is just called the amplitude and phase form. And it's just one of three different forms, and they're all completely equivalent to each other. So just each one contains the information a little differently than the other, but they're all completely equivalent. So which one you use comes with experience. Some people have a preference for one or the other. Also depends on what it is that you're trying to do. So hopefully as we go through this you'll get some feeling, but as you get into more advanced courses you'll learn more about this. Now, trig identities are abundant, and we can use those to apply to these cosines to transform those cosines into alternate forms, and that's how we get these other Fourier series. So let's take a look at how we do that. The first one, the first alternate form is called the complex exponential form. And hey, complex exponentials, we've already seen how useful those are. So this form is probably going to be a very useful form for the Fourier series. So I've just written out explicitly our amplitude and phase form that we started with, and calling your attention to Euler's form. So note, each one of these cosines can be broken into two different complex exponentials. That's the idea. So I'm just showing the first two terms, now circled, the first one in red and the second one in blue, and showing how the red one converts into these two different exponentials, complex exponentials, and this blue one also converts into two different exponentials. And again, this rectangular box is supposed to be a defined as. I'm going to make sure that that comes across in the posted notes. And one of these days I'll try to fix all this before I go on with too many more videos, but I'm on a roll. So now what we're seeing is that each single term gives us a positive frequency term and a negative frequency term. Positive frequency term, negative frequency term. And we notice that the coefficient here and the coefficient here are related. They're just complex conjugates of each other. So instead of having A1 and Phi1, we now have C1 and C minus 1. So two coefficients, two coefficients. Both of these are real. Both of these are complex now. Okay, so we can write this compactly like this with the understanding that A0 is equal to C0. So when we get to k equal to 0, notice this term goes to 1, and it works out just perfectly. And this is called the complex exponential form of the Fourier series, and this will be our workhorse. Okay, finally, we have the SineCosine form. And this comes, again, starting from the amplitude phase form. We apply this trig identity. You don't have to memorize it, but you have to look at it and go, yeah, I've seen that. Cosine of a sum of angles gives me cos, sine, sine. Yeah, I remember that one. Okay, so what that's going to do is take each one of these terms and turn it into a cos term and a sine term. So again, using my clever color coordination here, we see this cosine turns into a cos, sine. But notice that one of the cosines has a t in it and the other one just has a phase in it. One of the sines has a t in it, the other one has just a phase in it. So one of the coses turns into a coefficient, which we'll define to be A1. One of the sines turns into a coefficient, which together with that negative sign we'll call B1, and so on, and so on, and so on. So each cosine up here turns into a cosine plus a sine with appropriate amplitudes out in front. Interesting. And that leads us to something that looks like this. The DC term stays the same, so we still have that here. And this is our SineCosine. So what that's saying is that at each frequency we need one zero-phase cosine and one zero-phase sine. Notice that the a's, the little a's, and the little b's are real valued. So this is a nice form in the sense that we don't have to mess around with any phases, but the amplitude balance between each term, within each term at a fixed k, that amplitude balance, adding together a sine and a cosine, gives us exactly the right balance between those two terms to create what we want. And this just formalizes everything that we've seen, the relationship between these, and the boxes here tell us how to convert. So for example, suppose I have the exponential form, I've got the c sub k's here, and I want to convert into my SineCosine form. I need to get the a sub k's, but I only need them for positive k values, right? So the first thing I do is, but over here I've got c1 and c minus 1, so here's the trick. I need a sub 0. Well, a sub 0 is c sub 0. That's easy. I need a sub 1, a sub 2, a sub 3. Well, I just take the positive c sub k's and I take twice their real part. So a sub 1 is 2 times the real part of c sub 1. A sub 2, 2 times the real part of c sub 2. Now to get the b sub k's, I take the imaginary part of the c sub k's and multiply by minus 2. b sub 1 minus 2 times the imaginary part of c sub 1, and so on and so on. Now suppose we want to go backwards. Let's say that we have this and we want to get over to our beloved exponential form. So I've got the a sub k and the theta sub k. Again, these are going only over positive k's, and over here I need negative k's. So here's what I do. C sub 0 is a sub 0. C sub 1 is ak e to the plus j theta k. C sub minus 1, well, I should say it this way. C sub 1 is 1 half a sub 1 e to the j theta 1. C sub minus 1 is 1 half a1 e to the minus j theta 1. So the k's here go over just the positive ones that allow me to index these coefficients, but I get the positive and negative indexing of c's by having two different equations. So it's very easy to convert back and forth between these. Nice. So here's an example. I'll go through this quickly. It's pretty straightforward. Here's a simple three-term amplitude phase form, and we want to convert into the other forms. So suppose, picking off from here, here's our coefficients. In this case, we have a sub 0 is equal to 0, and I don't show that. So to convert to the complex exponential form, all we have to do is apply that formula that we were just talking about, and notice that we'll get a C1 and a C minus 1. In this case, we've got omega 0, 4 omega 0, 8 omega 0. So that's why we have the 1, the 4, and the 8. All the other a sub k are assumed 0. So you should be able to make these conversions, and then likewise we can convert into the sine-cosine form. So practice that during the in-class work. We'll be going over some examples of that and having you work on that. And that is the end of this lecture. Thanks.